So this is the starting page for all our resources, learning resources from the data lab. And I hope you are familiar with all these resources. And here you will find all the different notes for each of the workshops that are running this semester. So you can find them there. Also, the registration for each of the workshops. So today we continue with the classical machine learning, which is a yes, I'm going to share. Admit. Okay. So I'm going to share the general link, and then we go. Then we go to today's notes. And today's notes, we go in classical machine learning, and we were talking about scikit-learn, which is the library that is designed specifically for doing machine learning tasks. And today we are reviewing regression. So the materials will be here, and the notebook will be the next slot. So let's go into the materials. Just a very general introduction to regression using scikit-learn. And basically, regression has to do when we have a data set that is distributed for two variables, for example, and then we want to find a model that best fits the collection of data set. And there are many models, many types of models. The simplest one is just a linear regression, but we can find other models that we will see shortly. So we go into the materials for today's session. I'm sharing this link in the chat. And we will spend most of the time reviewing an example, how to do regression. So, okay. Okay, so there are different algorithms for doing regression. And the basic one is just linear regression, which is just the ordinary least squares method that we learned maybe in our previous courses. And the ordinary least squares guarantees that whatever curve we find for fitting a collection of data, the sum of the squares of the errors will be, can everyone hear me?
Yes.
Yes? Okay. Okay, so when you're doing the least square method, you are guaranteed that the sum of the squares of the errors will be minimum. And then that solution will be unique. And in scikit-learn, the way you import it into your code is just by calling sklearn, and then from the linear models, you import linear regression. There are other algorithms also. We have the stochastic gradient descent regressor. We have a polynomial regression when we know that probably the collection of data can fit an equation of higher order, maybe a quadratic, a cubic, quartic. Then we have the ridge and regression and lasso regression, which the only difference is how they compute the error. This is using the L2 or the squares of the differences, or just the absolute values of the differences. That would be the lasso. And elastic net allows us to do a combination between the ridge regression and the lasso regression. And then also we have logistic regression, support vector machine, decision tree learning, random forest. All these algorithms also have a regression algorithm. Okay. All right. So This is what I was talking about. You have a collection of data, and then you try to construct a model that they can fit to the collection of data sets. Okay. All right. So let's jump. Well, before we jump, also, how do you know you have a good fit? There's a collection of metrics you can use to see what is the error for each approximation or model. You have the R squared, the mean square error, the root mean square error, the sum of the squares of the residuals, the mean absolute error, and others. You can find all these different metrics inside scikit-learn. All these functions can give you an estimate of your error. Okay, so I have an example that we're going to spend the rest of the session reviewing it. So I suggest you can open this um, Jupyter Notebook in Google Colab, and once you open it, you will find it's yours. You can play with it. It will be stored in your Google Drive. I already have it open. So this is I'm just going to reconnect. The amount of computational resources is not very demanding, so you can run your your Jupyter Notebook in Google Colab just running with the standard computing resources. All right. So okay, so let's start. Okay, so as you may know, the first cell for best practices, I always put all the libraries that we are going to be involving and load them. So the first library is NumPy. NumPy is a Python library that has all the different algorithms for doing numerical computations. And we are going to denote it as MP. Then we have a plotting library, Matplotlib, and we're going to um, import the sublibrary pyplot, and we're going to denote it as PLT. So whenever you see PLT, it's calling the Matplotlib pyplot. And the whole library Matplotlib will be denoted as MPL. And then we're going to add some functions for pre-processing that are inside scikit-learn. We're going to import the add dummy feature. And then we're going to be importing all the different, well, this collection of linear models. We're going to be importing the linear regression, which is just the ordinary least square regression with the stochastic gradient descent regressor. The polynomial features when we're going to be adjusting a higher order equation into our data sets instead of a linear equation, maybe a quadratic. And then we're going to import the three other types of regressors, the ridge, the lasso, and the elastic net, which allows us to combine the ridge or the lasso. And some other functions to make pipelines. Okay, so we run the first cell. It's going to import into our working memory all these libraries, so now we can use them. And we'll start with the first example. So I want to generate points around the equation y equals 4 plus 3 times x. So that's going to be a linear equation that has value 4 when x equals 0 and has a slope of 3. And then we're going to use random function. We're going to generate random numbers. So we're going to generate 100 random numbers. And we're just going to be using the NumPy random rand and 100 points and one value. And we're going to multiply it by 2 just to have a random between 0 and 2. And then we're going to add this random number into the equation 4 plus 3 times x. So we will have just like a noisy equation around 4 times 3 times x. Okay, so I'm just gonna run it, and then we're going to plot. We're going to use matplotlib pyplot. We're going to plot a figure of size 6 and 4, 6 width, 4 units in height, and we're going to plot x and y in blue, the original x and y. No, yes. Well, x is now the random. So we're going to plot the x and y random numbers, and we're going to plot them, and then we're just going to plot axis. We're going to plot 15 points, and we just run the code, and we have this plot. Let me make it a little bit smaller. So this is the random set of points between 0 and 2, and the y values goes from 0 to 14. And so this is our, let's say, this is just the synthetic data we constructed, or we built those data sets using random function along a linear function. And now we're going to assume this is our starting point, and we're going to look for a model or a theoretical function that can fit best this collection of data sets. And by fitting best, using the least square method means that the sum of the squares of the differences between the real error and between the real value and the theoretical one will be minimum. So, okay. So let's start by that. So we're going to be using linear algebra to solve the equation for best parameters. So we can use, I'm not going to use scikit-learn yet. I can just use NumPy linear algebra library and try to find the values for the intersection and the slope. Okay, remember that we generated our data set using an equation that intersected in 4 when x was equals to 0 and the slope was 3. So if I now take the experimental data or synthetic data, I have that the intersection is 4.2 and the slope is almost 3. Okay. Then I can predict values. Once I have a theoretical model, then I can predict values that I didn't have. So I want to compute what is x when x equals, what is y when x equals 0 and x equals 2. And then I can predict the values. When x equals 0, y will be 4.21, and when x equals 2, y will be 9.75, more or less. Okay. Then I can plot that, right? Well, I need to compute this first. Oh, come on. I need to run every cell to use the next one. Everything is in sequence. So now I look at the plot, and here is the linear fit in red, and in blue, we have the experimental values. Okay, so this is this square fit for this experimental data or synthetic data, and in red is the line, the linear function that intercepts x equals 0 at value 4.21, and the slope is almost 3, 2.77. So this is my model. And then for doing regression, I can find what is the y value for whatever x I want to know. So so this linear function or model can predict or can do a regression for any point. Okay, so we did this example just using linear algebra, as we as we know from our previous courses. And now we're going to use linear regression algorithm from scikit-learn. Okay, and the function we're going to use is called linear regression. And we're going to define the model called lins underscore reg. This will be the name of the model. And then I'm going to fit my model using X, which is the collection of random samples, and Y. And then once I do the fit, then I'm going to compute or ask what are the values of the interception point and the linear regression coefficient or slope in this case. So I execute this line, okay? And this, so the array, the interception is at 4.21 and the slope is 277, which agrees exactly with what we did before, 421 and 2.77. So doing using linear algebra or using linear regression from scikit-learn, you get the same results, which is the same function. Okay, and then I can predict what are the values of x at x equals 0 and x equals 2, and I get similar values that I got from my previous linear algebra example, right? These two values. Okay. So nothing new, except that now we are using the linear regression function from scikit-learn. Okay. I have an example here how to do it using linear algebra, the least square method from before. And well, if somebody is interested in another way of doing it, so using the function least squares from linear algebra from NumPy and try to solve the equation for xp, which contains the intersection point and slope, and there is a condition of iteration or error. I want an error less than 10 to the minus 6, and I get the two results, okay, using this function from linear algebra NumPy. So I'm not going to repeat that. And basically what we are doing is we have this matrix XB equals the matrix of elements PM, and the matrix X being this matrix of 1 and X. So Y is just the intersection plus the slope times X, which is, if you write it as in a matrix form, will be this way. So this is the product. Y equals the product of these two matrices. And then you solve for Y. You have to multiply by the inverse of matrix XB. And X will be just the inverse of the B matrix times Y. And then you can solve using linear algebra and you get that result. Okay. So it's the same thing if you use linear algebra or you use the linear regression function from scikit-learn. Okay. Okay. Now we can do it using a different method, the gradient descent method. The gradient descent method is just imagine that you are on a hill, and the gradient descent method will take you to a path that you're always going into a valley, okay, from a mountain into a valley. That new algorithm will have a learning rate, or you can say it's the step size. And then we're going to run for 1,000 iterations. And we're going to create 1,000 points and see where does the algorithm converge. And the algorithm will converge theoretically to the values of the intersection point, and the slope. So I'm just going to execute it. Again, yes. Okay, so let's do it. So the theta, which are the parameters for the linear equation, gives me again the same intersection point and the same slope for the same collection of data. Then we can plot the gradient descent method, and We execute the code. And basically, this is how, so we have like an initial line in light yellow. And then as the algorithms is iterating, the solution is getting near and near and near into a unique solution or the final iteration, which is this equation. So this is another way of doing the approximation or the regression. So we start with a family of lines which are converging into a final line which is in red. Now I have here an overlap number of plots, so it's difficult to see, but will be the end state. So that's using the stochastic gradient descent method. That's another way of doing it. And I get the same values for the intersection and the slope. So this is using the stochastic gradient descent. And then I will do, I will use scikit-learn to do the same thing. And the algorithm is called STG regressor algorithm. And here I will say you can do up to 1,000 iterations, and the tolerance or the error will be 10 to the minus 5. There is no penalty. The eta is just like the learning step. The number, when there is no change, is going to be 100. And for reproducibility, we will use random state or like a random seed, 42. So every time we do this equation and that we are involving random numbers or pseudo-random numbers, we always get the same result. And then for this model, we're going to fit the values of x, y. And we execute this. And this is the model now fitted. And then we're going to ask what are the interception point and the slope. And I get the same result. The interception point is 421 and the slope is 277. Okay, so that's a couple of algorithms to fit a collection of points that we generated synthetically around the equation of 4 plus 3 times x. Now I'm going to now pass to a higher order equation. So now we have the polynomial y equals 2 plus x plus 1/2 of x squared. So this is a quadratic equation. When x equals 0, y equals 2. So the interception point is 2, and the coefficient of x is 1, and the coefficient of x squared is 1/2. But I'm going to generate synthetic data around that equation using a random number. So x will be, I'm going to do 100 samples. X will be 6 times a random number minus 3. So that's going to be x, and y will be, well, this equation, 1/2 of x squared plus x plus 2 times plus the noise, the random number that we're going to be generating. Okay, so we're creating noise around x and adding y, yeah, to add the equation y. So we generate this, execute, and then we will plot again. So I get these numbers. So I have synthetic numbers or equation on that data generated along the equation above here with random numbers. 2 plus x plus 1/2 of x squared. All right. So now we know that this was generated with a quadratic equation with a little bit of noise. And then the next thing we want to do is, assuming this is our experimental data, I want to fit a polynomial to this collection of data sets. And for that, I'm going to use scikit-learn, and I'm going to use the polynomial feature function. And so I'm going to call this polynomial feature function degree 2, meaning a quadratic equation. I'm not going to include any bias, and I'm going to compute the polynomial and find what is the value of the first at x equals 0. Remember that at x equals 0, our theoretical function was equals 2. When x equals 0, y equals 2. So I do this. It's very far apart, but that's okay. And then we can ask what are the coefficients for the coefficient of x is almost minus 0.75, and the coefficient of the x squared is 0.566. And then for these values of x, I'm going to fit first a linear regression. But now I have a polynomial. And I have the coefficients. The coefficient, independent coefficient is 178, and the coefficients for the x is 0.93, and for the x squared is by 0.56. So this is the fitted polynomial to my collection of data sets. Okay, so this is the best fit using linear regression, using a polynomial function to the collection of data, which is this one. And now I can probably plot it. Yes, I plot it. So I'm going to plot this polynomial, the fitted polynomial, and also show the fit to our collection of data. Okay, so we're fitting a second order equation or second order polynomial to the collection of points. Okay, so when you have in real life, when you have a collection of data, you can try to fit whatever polynomial degree, and when you compute the errors, you're going to select whatever polynomial has the least size of errors. So in this case, if I try to fit a linear equation and I compute the error, for the linear equation, I will have more errors than if I fit a second order. The same way, if I fit a third order equation or a fourth order equation, my error will be larger. So least squares method, you always select the one that the error is less. Any questions up to here? So this is just our basic regression for a collection of data. And we started creating a collection of data synthetically by taking a linear equation and then a quadratic equation and adding some noise. So we can mimic an experiment that gives you this collection of data. And then we used scikit-learn to get a linear fit using the least square method, and then we use polynomial function to adjust the quadratic equation. Questions? This is standard materials probably for everyone, but it's part of the collection of functions that you can find inside scikit-learn in order to do regression. Okay. Now I'm going to go further. So I'm going to fit different degree polynomials to my data set and see how it goes. Okay. So again, I'm going to let's see. Okay. Right. So we'll have, um, I'm going to plot, all right. So here I'm going to plot in red using plus signs, an equation of first order. In blue with dash dash lines, I will plot an equation of second order, and in green with just single dash, I'm going to plot an equation of degree 100. This is just exaggerated. And then we're going to use polynomial features for the three equations of order 1, order 2, and order 100. For polynomial of order 1, which is a linear equation, polynomial of order 2, which is a quadratic, and this is a 100 order polynomial. And I'm going to do a loop, and for every degree, I will use the polynomial features, and I'm going to define my model, standard scalar, and do the linear regression, and then I'm going to be fitting the polynomial, and at the end, I'm going to plot all the different polynomials, okay? So execute this, yes, and then this creates my, so this in blue is the collection we had before, which we fitted a quadratic equation, remember? Now it's in blue. And this is the linear equation. What if we fit a linear equation to our data set? It looks like this. And then I fit a one polynomial of order 100 to my data set. And you can see all these oscillations and overfitting, right? And when I compute the errors for any of the fits or any of the models, I will find that the quadratic equation has the least error. So I pick the second order equation to fit my collection of data set. And the error committed by using a linear equation will be larger. And the order uh, committed when we are using a polynomial of order 100 will be larger. So your choice is to select the second order because it will have the least square error. Any questions? No? Okay, seems like this is a very easy material. Okay, so now let's go to another collection of regression algorithms. The first one will be the rich regression. Remember, you can always assume using the most simple. So how do you select which is the best? The best one will be whoever model has the least error. Okay, so when you take the differences between the experimental dot and the theoretical function, and then you sum the squares of the differences for the dotted in blue line, you will find that the error is less than if you compute the errors between the red line and the experimental dots. So if you sum the squares of the errors, in this case, the one that will fit, it will have the least error. And the other two choices will have larger errors. That's how you select which is the best, okay? So it's not by seeing what is, or there's nothing to guess. If you compute the error, you will get a number, and you take the model that has the least error, and that's the way you can choose. Okay, all right. So we continue. So now we have another regression algorithm, but this way, in this method, the rich uses the L2 regularization. L2 means it's just a quadratic of the differences, the square of the differences. And You can use it whenever you have high dimensional data. It's more resistant to noise. It can add some small biases because you're trying to minimize the squares of the differences. And so that's how you can use it. So here we are going to approximate a function 1 plus 1/2 of x. We're going to use a random seed, a random 42. So if you keep this number, every time you run it, you will get the same result. If you forget that or you put some other number, you will get a different result. Okay, so I'm going to generate 20 points. And x will be 3 times the 20 random points. And y will be 1 plus 0.5 times x, which has some random part, plus another random term divided by 1.5. And we'll create an x axis, which is just 100 points between 0 and 3. And using the function from NumPy linspace, just generates a matrix or an array of 100 points between 0 and 3. And then, so we have x and y. And then we plot what we generated, okay? Again, we're going to be using pyplot from matplotlib. This is how we're going to plot x versus y, just a scattergram. This is how you put the labels to the x and y axis. And you can rotate the text of the y axis. We're not rotating. And you can put the title and plot the axis, add a grid, and show the result. So we execute. And we have this, oh, maybe I didn't, yes. Okay, so these are my random set of points, which is 20 random points. Okay. Now the next task is try to fit a model to this collection of data. And we're going to be using the rich regression algorithm. Okay. And we will use different parameters, alpha, and also a solver. We can have different solvers. Okay. If you put it auto, it will decide what is best. Or you can force a specific solver, in this case, Cholesky. You have single value decomposition, the least square, sparse, I don't know what is Saga, and this other algorithm. Okay, so we're going to use Cholesky and alpha equals 0.1. And we're going to use the function rich, which is the rich regression from scikit-learn. And we define the model with rich underscore reg, and then we're going to fit to this model the values of x and y, and try to predict the value at 1.5. So we execute. This will be the value at 1.5, value of y. And then let's say we're going to plot different regressions for different values of alpha, and we're going to plot them. Okay, so I'm going to be changing different values of alpha. Okay, and the alphas that we're going to be plotting is alpha equals 0, alpha equals 10, and alpha equals 100. And this is what comes out. Using a linear regression fit and using a polynomial regression fit. And these are for the different values of alpha. Okay. And in blue, the dots in blue is our experimental data or generated synthetic data. And in red is going to be with alpha 100 in the left-hand side and alpha equals 1 on the right-hand side. And in dotted blue is alpha equals 0. And in dash green is going to be alpha equals 10 and alpha 10 to the minus 5. You can see if you're doing a polynomial regression, we used smaller values of alpha. And in the linear regression fit, we used large values of alpha. And also alpha equals 0, it will coincide with the linear regression, but it is not advised to run ridge regression using alpha equals 0. If you're interested in knowing the alpha equals 0 case, then you just use the standard linear regression. Okay, and then what is the best fit? Again, you have to go and compute the error and select whatever error is minimum, or select the regression which has the least error. Okay. Another way of doing this is the stochastic gradient descent regressor. And I'm not going to spend too much time because I want to see the other method, the lasso. And you can see what is the result of the fit. And these are the coefficients. Okay. All right. So I didn't plot anything there. The other method is the lasso regression. So the lasso regression, instead of doing the L2 regularization, it does the L1 regularization. And the L1 regularizations uses just the absolute values of the penalties. Okay. And when to use the lasso regression? Again, when you have high dimensional data that requires some feature selection, and when the model interpretability is important. In this case, if you use rich, then all the features or all the dimensions or all the variables have more or less the same relevance. And if you're using lasso, maybe you will find that some variables are more important than others. So the method will try to minimize the influence or the impact of the variables which are not very relevant. So that will be the difference. Okay. It's going to reboot. Okay, so now we do the gate again. Lasso is just the name of the function. We define the model as lasso reg. We're going to fit the model into x and y variables, and we're going to predict what is the value at x equal 1.5. Again, we get 1.53, which is the same value we have found with the other methods, 155.3. Okay. All right, and then we will do the regression for different values of alpha. Okay, and we're going to plot. And see, this is the lasso regression fit for different alphas. In this case, small alphas, alpha equals 0 coincides with the linear regression. Alpha 0.1 is in green, and alpha equals 1 is in red. And using the linear regression fit and using a polynomial regression fit with lasso for these values of alpha, 0.01 and 1, you have this collection of plots. And again, which is the best fit? The best fit will be that has least error, least error. Okay. So that's your criteria for selecting. But here you are showing different regression functions. Okay. Now, the next algorithm, elastic net, allows you to do a combination between lasso and and reach. So you will have a combination of using the L1 normalization and L2 normalization penalties, and then you will have a parameter which will control the mix between the L2 and L1 penalties. So alpha in this case will be what is the relevance of one method or the other. And so if you're using elastic regression, you can identify and potentially remove irrelevant features by setting their coefficients close to zero. And also, you can also handle multicollinearity. And this is an example. Again, we're using the elastic net, and we're using a combination of lasso and reach of 0.1, ratio L1 ratio 0.5, and this is the model. We feed the model into X and Y collection of data, and then we predict what is the value 1.5, and again is near 1.55, which was obtained with the other methods. Okay, so if you're not sure if you should use lasso or reach, you can use elastic net and play with the alpha combination. Okay, and you can see that the predicted value for x equals 1.5 is almost the same one that we have been obtaining with the other methods. Here we had 1.53, and in this case we had 1.55. So this was reach, that was lasso, and this is elastic net. So we're trying to predict a value. Another regression algorithm is logistic regression, and it's also used in some other applications, but it is it allows you to classify data into discrete classes and also make binary predictions, yes or no. And we will see it later, but I'm just going to plot what is the logistic function, which is a sigmoid. And a sigmoid function is just has value of 1 if x equals, if x or t is tending to infinity, and it's equals to 0 for large T negatives. And it's going to be, this allows us to make decisions. If it's T, if T is positive, then it goes on the right-hand side, and if T is negative, it goes to this part. Okay. Now, before we end, I'm going to talk a little bit about metrics. So this is the criteria where you select, or helps you select which model is best. And you have the R2 score, which computes the coefficient of determination, and it's denoted by R squared. So if you have different regressions, you can apply R2 score and see which one is better. Or you can compute the mean absolute error, or you can compute the mean square error, or you can compute the mean absolute percentage error, or you can compute the max error, or you can compute a collection of those metrics and see what is, and then you decide what criteria you use to stay with one regression or the other. And well, and this is how you compute all the metrics. So from scikit-learn metrics, we import the function mean square error, and we have an expected value and a predicted value. Then we compute the errors. Okay, and we plot we print the errors here. Okay. This is the errors. The mean square error between the predicted and the real value. So this is the error. So the error is larger when the predicted value is close to 0. Okay, an example of a root mean square error. Again, you call the function mean square error and then compute. It's going to be a number. Oops. Something. Yes. Mm, okay. I learned that here. Anyway, gonna skip it for now. In the same way you apply the other metrics. Okay. All right. So I know it's too much information again. Sorry for that. But I tried to do an example of how to do regression. The question. Elastic outperforms lasso or reach. Uh, Elastic is a combination of lasso and reach. So it's you're using both sides, both regressions. So you can say it has an advantage of not using one or the other, but using a combination can give you a better or least a smaller error, and also take advantages of how you can select or find out which variable or which feature has more relevance than the other ones. Yes, it has some advantages than using just only one of the previous two. Okay. All right. If there are any other questions, please let me know. And if not, then next week we will continue with um, classification algorithms using scikit-learn. And that's what I have for you today. Thank you. Thank you for connecting. And we'll see you next week.